Welcome to the Walton Pi. This is a linear algebra test review where we talked about eigenvalues, eigenvectors, bases, and null spaces. Do you have any questions for me? Or would you like to be sure that we go over?
Specifically, anything with eigen in front of it.
Anything eigen?
Yeah.
Okay. Yeah, I'll make a note of that. We can definitely go over some of those. Alright. Alright, did you have anything else that or shall we just start with that?
I think we can start with that. I do want to let you know, though, like, I'm really solid on finding determinants of matrices. Like, that's not the issue. It's, like, understanding the concepts of eigenspaces and eigenvalues and how to find the actual math of doing the determinant, that I understand.
That is straightforward. It's just figuring out what the eigenvectors and eigenvalues mean.
Yeah, or, like if I get an eigenvalue, how do I get an eigenvector out of it?
Okay.
Or how do I find things like that geometrically? Like, I don't
Okay.
understand.
Yeah, so let's start by just defining what those different values are. So an eigenvector, this is any vector. So if it's an eigenvector, it satisfies the matrix times the vector is equal to some scalar times the vector for some scalar lambda. So an eigenvector is any vector that satisfies that under the assumption that the vector is not the zero vector. And so this is going to be the definition of an eigenvector, and so this lambda, that is called the eigenvector, or not the eigenvector, the eigenvalue. And so those are the two main things that have eigen in front of it, eigenvector and eigenvalue, and they all come back to this relationship. And so if we look at this relationship, that gives us an idea of what or how we can visualize these graphically. So for example, if we were to be looking on some graph, and if these black vectors are our original vectors v, so let's just draw a few of these. So if these are original vectors v, so black are v, and then let's say that the red vectors are going to be a times v. So we look to see what are those after the transformation. If we say that all of them are going like this, so I'm just drawing them from the same the ending point of the last vector. The question is, which of these vectors are going to be eigenvectors? If we go back to the definition of an eigenvector, it says that the matrix times the vector, so this a times v here, is equal to some scalar times the vector. So we are looking for the vectors where the transformation, so the red version, so a times the vector, is just a scalar multiple of the original vector. So it's a vector that is pointing in the same direction as its original vector. So it's pointing along the same line. So the highlighted vector there is going to be our eigenvector in this diagram, because the transformation of the vector is still pointing in the same line as the original vector. Did that make sense as to like geometrically what it means?
Yeah, so it's, if you have a bunch of vectors, it's going to be the vector that, like, because A transforms all of them, and so it's going to be the vector that its transformation is a scalar multiple of
Yeah.
Okay.
Yeah, and so if we were to, so this would be our eigenvector. If we wanted to then figure out what the eigenvalue would be, we'd have to estimate about how much did it stretch or compress the vector. So we would look to see, well, that's our original length, and we got about 1.5 of those. So we would probably say that lambda is about 1.5 for that vector v. And so that's just saying how much do we stretch it under this transformation. So geometrically, that's what this is. And the reason we care about them is because it's easier to multiply a vector by a scalar than to do matrix vector multiplication. Scalar, there's just one quick calculation, whereas matrix multiplication, you have a whole bunch of different calculations to be able to do it. And so a lot of what you talk about with eigenvectors and eigenvalues in this class are ways to be able to solve problems by turning it into eigenvectors, because those calculations are much faster for a computer to do. And so the upfront computations to find the eigenvectors and eigenvalues are worth it because it saves time overall. So that's why we care about them. It's the only reason we care about them is because they have this very special property. So then if we were to want to try and figure out what the eigenvectors and eigenvalues of some matrix are, let's say that we had the matrix A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to find the eigenvalues, the way we can try and remember this is we know that if we do A times a vector, that's going to be equal to lambda times a vector. So A times V minus lambda V is equal to 0. So if we want to try and factor out the V from this other side, we would first have to insert an identity matrix so that we can be able to successfully factor it. Because when we factor it, we would get A minus lambda I times V. If we didn't have this I term, then what we would have is we'd have a matrix minus a scalar. And that's not allowed. We have to be subtracting objects of the same type. So to pull out the V, we had to insert the identity matrix in order to be able to factor it completely. And so if we then get A minus lambda I V is equal to 0, this is telling us that eigenvectors, those are in the null space of A lambda I. And so that's how you can find your eigenvectors. So what we're going to do is we are going to solve for what values of lambda give us a null space that is not just the 0 vector. And so that's why
we set the things to 0.
Yeah, so that's why we set it to 0. We look at A minus lambda I. So we get 1 minus lambda, 2, 3, 4, 5 minus lambda, 6, 7, 8, and 9 minus lambda. And so what we're trying to do is we are trying to figure out what values of lambda make this matrix have a non-trivial null space. And the way that we do that is if the determinant of A minus lambda I is equal to 0, then the null space is bigger than just the 0 vector. And so that's what we care about. We want to figure out when is the null space more than just the 0 vector, because the 0 vector is always in the null space. So we want non-zero vectors in order to get an eigenvector. And so that's why we look at the determinant of A minus lambda I, and we set it equal to 0 to solve for lambda. We're trying to figure out what eigenvalues give us a non-trivial null space. So if we look at what's the determinant of A minus lambda, that's going to give us 1 minus lambda times, we got 5 minus lambda, 9 minus lambda, minus 48. Let's see, minus 2 times 4 times 9 minus lambda, minus 42. And then plus 3 times 40 minus 5 minus lambda, times 7. So that's going to be the determinant, and we set this equal to 0. And our goal now is to solve for what lambdas are going to make this determinant be 0. And so that's why we go through that process to figure them out. So whatever lambdas we get are going to be the eigenvalues, and then from there we can find the eigenvectors. Now, this one looks like it's going to be a bit nasty, so I'm going to switch to a different matrix A just to make the process a little bit easier and a bit more straightforward. So here we are going to say that A is going to be the matrix 1, 2, 3, 0, 1, 2, and 1, 3, 5. So if we go through and do this process, we would find that we get lambda equals 1, and lambda equals 0. You could go through the process and check that, but those are going to be the eigenvalues of this matrix. Wait, nope, sorry. That is incorrect. Let's actually just go through it. A minus lambda I. So let's just subtract those lambdas here. So minus lambda, and minus lambda. That is going to be 1 minus lambda times 1 minus lambda, 5 minus lambda, minus 6. Plus 1 times 4 minus 3 times 1 minus lambda. So let's see, expanding all that out, we get 1 minus lambda times 5 minus 5 lambda minus lambda, so minus 6 lambda, plus lambda squared minus 6. Plus 4 minus 3 plus lambda. So that's going to be, let's see, 5 minus 6, that becomes a negative 1. And then distributing the 1 minus lambda, so we get a negative 6 lambda plus lambda squared minus 1 plus 6 lambda squared minus lambda cubed plus lambda. 4 minus 3 is 1, so that's a plus 1 plus lambda. And all of this is equal to 0. And so now our goal is to combine terms and try and factor it. So let's just rewrite this a bit. So negative lambda cubed. We got 6 lambda squared plus lambda squared, so that's plus 7 lambda squared. We got minus 6 lambda, so that's minus 4 lambda. And then minus 1 plus 1, so that's a plus 0. So all of this is equal to 0. So we can factor out a lambda to start. And then at this point we would need to go through the quadratic formula to figure out what the other lambdas would be. But I don't really want to go through and figure those out, but we could go and do them. But this one tells us that one solution is going to be lambda equals 0. And so once we have that, we are going to then go back in and figure out what is the null space of A minus 0I. Because 0 is our lambda value. So we are looking at the null space of 1, 2, 3, 0, 1, 2, 1, 3, 5. Yeah, did you have a comment?
Yeah, so let me just say this so that I can make sure I'm thinking about it right.
Uh-huh.
So sorry, I dropped my pen. Anyways, but so it's the same thing as it was before, except now we're plugging in the lambda values that we found, right? Continue.
Yeah, so we're plugging in the lambdas that we found. So we found one lambda was lambda equals 0. And so plugging that in, we're now trying to figure out what's the eigenvector or eigenvectors that correspond to that eigenvalue. So we are looking for the null space of A minus lambda I. So we can find the null space by row reducing the matrix. So we can start with 1, 2, 3, 0, 1, 2, 1, 3, 5. Well, that row reduces to 1, 2, 3, 0, 1, 2, 0, 0, 0. And we could continue on with this and move it all the way into reduced echelon form if we wanted. So we'd get 0, 1, then a 0, and then 3 minus 4 is a negative 1, 0, 1, 2, 0, 0, 0. So we are looking for the null space of this last matrix because the null space of row-reduced matrices stay the same. It doesn't matter what row operations you do, the null space stays the same. And so what we would do is we would look to see how many free variables are there in this row-reduced matrix. In this matrix, we have one free variable in our very last. So if each column corresponds to x, y, and z, this tells us that z is free. I often like to write this as z equals z, just to say z can be any value I want it to be. But then x and y are going to be in terms of z. Because if we look at the null space, each of these rows are going to give us a different equation. So this first row, that's going to tell us that 1x plus 0y plus negative 1z is equal to 0. And the second row is going to tell us that 0x plus 1y plus 2z is equal to 0. From both of these equations, we can then be able to solve for, from the first one we get x equals z, and the other one is going to be y equals negative 2z. So we have z equals z, x equals z, and y equals negative 2z. So that tells us that our vector is going to look like z, negative 2z, z. I should put dashes to distinguish them from 2's. And so this is going to be our vector. Anything that looks like that is in the null space. So to find an eigenvector, you would pull out the v. So our vector is going to just be 1, negative 2, 1. Because that is, any vector that is a scalar multiple of this is going to be an eigenvector. And so that's how we would find our eigenvectors. It's 1 minus 2, 1 times z, which is our free variable. So this is what's left over, is one of our eigenvectors.
And that's the eigenvector that corresponds to when lambda is 0.
Yeah, so this would be like vector 1 with lambda 1 equaling 0. So that is the vector that corresponds with 0.
Okay, and then the span of that eigenvector is the eigenspace, right?
Correct. Yeah, so the span of this vector is going to be the eigenspace, and all of those vectors except the 0 vector are also eigenvectors. The only reason 0 is not an eigenvector is because it's defined to not be an eigenvector. And we can go back and check this because that vector, if we go back to our original matrix A, if we look at 1, 2, 3, 0, 1, 2, 1, 3, 5, and multiply it by the vector 1, negative 2, 1, you will find that this is going to give you the 0 vector. And so that's how you can be able to go about finding the eigenvector for a given eigenvalue.
This is kind of going backwards, but could you remind me what null space represents? Like, what is a null space of a matrix?
Yeah, so the null space of a matrix, so if we're looking at the null space of some matrix A, this is equal to the set of vectors, so it's the set of vectors V where the matrix times the vector V is equal to the 0 vector. So any vector, so if A times x is equal to the 0 vector, then x is in the null space of A. So the null space is just the set of any vector that when multiplied by A gives you the 0 vector.
Okay. Alrighty, thank you.
Yeah, and so from this is where we're able to quickly see that if x is the 0 vector, then A times the 0 vector, that's always going to give us the 0 vector. So that tells us that 0 is always in the null space of A.
Gotcha, thank you.
You're welcome. Yeah, did anyone have any other questions with this or other things that they'd like to talk about?
So in theory, there are 2 more values that we would get for lambda after doing the after we find the roots. Is that true?
That is true. So if we went back to like when we were factoring this, there are going to be 2 other roots that we would be able to find. So we'd also be able to say, so looking at this term, the quadratic formula would tell us that we also would have lambda equals, what's the opposite b, so that's 7 plus or minus the square root of b squared, so that's 49, minus 4 times a, so that's 4 times 1 times 4, all over 2 times 1. So that would be 7 plus or minus the square root of 49 minus 16, square root of 33, all over 2. And so those are going to be our other 2 eigenvalues, which you could then go through the process and find your eigenvectors. But because those have square roots, I'm not in the mood to try and do those on camera because I know I will make some arithmetic errors. But there would also be an eigenvector corresponding to each of those eigenvalues as well. Yeah. Anyone have any other questions for me?
If no one else wants to ask a question, I'll ask another one.
Okay.
Can you go over linear transforms?
Mm-hmm.
Just like a basic overview, you know?
Yeah. So a linear transformation is something that has so that is massive text. All right, so a linear transformation is anything that satisfies the following restrictions. So it's anything that satisfies a times x plus y is equal to a times x plus a times y. So that's the first requirement for it to be a linear transformation. The second is, let's say that where those are vectors. The second is that a times a scalar times a vector. We can pull the scalar out front. So that's the second requirement. And then the third one is that a times 0 is 0. So those are the requirements for something to be a linear transformation. Anything that satisfies all 3 of those are going to be considered a linear transformation. So matrix multiplication is one example of a linear transformation. It is not the only one, but it is an example, and it's the main one that you're covering in this class. But there are going to be other things that are also linear transformations. An example is taking derivatives. If you remember that from calculus, taking derivatives is a linear transformation. But that's not something that you need to care about a ton in this class, but just remember that matrix multiplication is not the only form of a linear transformation. So this is the definition. From there, so let's go back here. From there we can be able to figure out if something is a linear transformation or not. So for example, let's say that we have t of xy, so t times the vector xy, is equal to the vector x plus 1, y minus 2. If this is a linear transformation, then it has to satisfy all three of those properties. So to check if something's a linear transformation, we just have to check each of those different properties. So one thing that we can do is we could say, well, t of b, well, that's going to be a plus 1, b minus 2. And so if we look at what is t of x plus a, y plus b, this is t of xy plus ab. So if this is a linear transformation, we would then have to see, is this actually equal to t of xy plus t of ab. So if we look at t of x plus a, y plus b, that's going to be the vector x plus a plus 1, y plus b minus 2. And we are saying, is that equal to x plus 1, y minus 2, plus a plus 1, b minus 2. And it turns out it's not going to be, because this is going to be x plus a plus 2, and this is going to be y plus b minus 4. And so because these are not equal, this is not a linear transformation. And so that's what you can go through and do to figure out, is this going to be a linear transformation or not? If something is a linear transformation, then we're able to write it as a matrix. So something that would be a linear transformation would be a of xy is equal to x plus y, 3y minus x. That is a linear transformation. If you want, you can go through and check all three of the conditions, but all three of them are going to be met. So this is going to be an example of a linear transformation. And so we might want to say, well, what's the matrix of that linear transformation? And so this is where we then have to say, okay, what's the basis of our system? Because in order to have a matrix, we need to have a basis. So we often say it's the matrix with respect to the basis, and then we give a set of vectors, which are going to be the basis we're going to use. So because this is a two-dimensional vector, a common basis is to pick 1, 0, and 0, 1. And so we want to figure out what's the matrix of transformation with respect to this basis. And so one way we can figure out what the matrix would be is we can start with the matrix with our basis elements. So our basis elements are going to be 1, 0. So there's one basis element, and then the next one is 0, 1. So I drew those little lines just to signify that they're there, but they're kind of just pretending. We don't really draw those, the vector form there. We're just way of signifying we are writing these in terms of columns. Because if I didn't specify they were columns, some people often read them as rows. That is not what we're wanting. We are putting the basis elements as the columns. And so now what we want to figure out is we want to figure out what do these columns turn into under this transformation. And this is going to give us the matrix of that transformation. And I'll show you why in a second. So if we look to see what is A of 1, 0, well, that's going to be the vector 1 plus 0, so a 1, and then 3 times 0 minus 1, so 1 minus 1. And A of 0, 1 is going to be 1, 3. So that tells us that the matrix A is equal to 1, negative 1, 1, 3, where we replace the columns of our basis with what they turned into under the transformation. Another way we could have approached this is we could say, well, how many x's and how many y's does it take? Because we could look at the matrix A and we can say, well, it's a 2 by 2 matrix. So unknown values go there and there. And when we multiply it by x, y, we are going to get the vector x plus y and then 3y minus x. Well, how do we get x plus y right here? That is going across here multiplied by this. So it's whatever this is times x, so there's one of those, plus whatever the second box is times y. So that's going to be also one of those. And then the next one would be, well, how do we get the 3y minus x? Well, that is this second row times that column. So that's where we get a -1 of the x's and a +3 of the y's. That's a second way that we can figure out what's the matrix of that transformation. Did that answer your question with this? Or are there other questions that you would then like me to answer?
I'm good with it.
Okay. Let's see. Anything else with vector spaces or determinants or eigenvectors anyone would like to touch on?
Nothing in particular. I would just like to see another example.
Okay. Another example of finding the transformation or of finding eigenvectors?
Eigenvectors and eigenvalues.
Yeah, let's go through and do one of those. All right, so let's say that we are with the matrix 1, 0, 3, 1, 1, 2, and 0, 1, 7. And this is A. And we want to find all the eigenvectors and all the eigenvalues. So to find our eigenvalues, that's what we want to do first. We are going to look at determinant of a minus lambda I, and we want this to be equal to 0. So a minus lambda I is going to be the matrix 1 minus lambda, 0, 3, 1, 1 minus lambda, 2, 0, 1, 7 minus lambda. And so the determinant of that is going to be we got a 1 minus lambda times uh, 1 minus lambda, 7 minus lambda, minus 2. Then we have plus 0, or I guess minus 0 if we're sticking with the rule to find the determinant. So minus 0 times something, and then plus 3 times 1 minus 0. Perfect. That's going to be an easy one. So this is going to be equal to, we got 1 minus lambda times 7 minus 8 lambda plus lambda squared minus 2 plus 3. So that is 7 minus 2, that's going to be a 5 in there. So let's see, so we got 3 plus 5 minus 8 lambda plus lambda squared minus 5 lambda plus 8 lambda squared minus lambda cubed. So we got a negative lambda cubed. We have 8 lambda squared plus lambda squared, so that's plus 9 lambda squared. We got minus 5 lambda minus 8 lambda, so that's a minus 13 lambda, and plus 8. And so we need to figure out how can we factor that cubic polynomial. Let's see, are there any nice ones? This is the problem with coming up with things on the fly. They might not always factor. see, does 2 work? Negative 8 plus 36 minus 26 plus 8, that doesn't work. Negative 2, that'd be 8 plus 36 plus 26 plus 8, that definitely doesn't work. Does that factor nice? I am starting to be skeptical of that. So factor x cubed minus 9x squared. Alright, that one does not factor nice. So we do not want to do this one, so hopefully they wouldn't give you something like that on the test. But there are no easy factors, so let's do one that's definitely going to have easy factors. Okay. Let's do 1, 1, 0, 1, 0, 1, and then 2, 1, 1. This one's going to at least be able to be factored. So that is A. So A minus lambda I, that is 1 minus lambda, 1, 0, 1, negative lambda, 1, 2, 1, 1 minus lambda. Okay, so then the determinant of A minus lambda I is going to be, we have 1 minus lambda times negative lambda, 1 minus lambda, minus 1, minus 1 times 1 minus lambda, minus 2, and then plus 0 times 1 plus 2 lambda. So this is equal to 1 minus lambda, let's see, lambda squared minus lambda minus 1, minus, let's see, 1 minus lambda minus 2, that's negative lambda minus 1, plus 0, so plus, plus, plus. So let's see, this lambda cubed, whoops, my mistake, lambda squared minus lambda minus 1 minus lambda cubed plus lambda squared plus lambda plus lambda plus 1. So that is negative lambda cubed plus 2 lambda squared minus lambda plus lambda plus lambda, so that becomes a plus lambda, and then plus 0. So we can factor this. We got negative lambda times lambda squared minus 2 lambda minus 1. And at this point we can go through and use the quadratic formula to figure out what the other two factors are going to be. So those are going to be 2 plus or minus the square root of b squared, so 4 minus 4 times a is 1 times c is a negative 1, all over 2. So this is 2 plus or minus the square root of 8 over 2, 1 plus or minus 2 root 2 over 2. So this is going to be 1 plus or minus root 2. So those are going to be our different eigenvalues. So we have lambda 1 equals 0, lambda 2 equals 1 plus the square root of 2, and lambda 3 equals 1 minus the square root of 2. Does that make sense to everyone?
Yeah, would 0 also be 1 since you have the negative lambda up in front?
Sorry, say that one more time.
Sorry. Would 0 also be one of the values just at the up front in our factoring?
So the 0 came because we had this negative lambda in the factor, and so we were solving for where are each of these factors 0, and so that's where this lambda 1 equals 0 came from.
Gotcha. I see. Sorry.
Oh, you're totally good. Yeah, any other questions that people have? Okay. So at this point, what we can do is we can go through and try and figure out what vectors are in the null space of each of these eigenvalues. So let's clear this a bit so we can figure out the vectors that correspond to it. So one of the vectors is going to be pretty easy to compute. That's going to be for the lambda equals 0, because that's a nice one to be able to deal with. But then for the others, it's going to be a little bit more complicated, but it's still going to be doable. So if we're looking at lambda 1 equals 0, we're looking for the null space of the matrix 1, 1, 0, 1, 0, 1, 2, 1, 1. So we are going to row reduce that matrix in order to make it simpler to solve. And so it's going to row reduce to 1, 1, 1, 0, 1, 0, 1, 0, 0, 0. And so then we get that a little bit further to 1, 1, 0. Subtract the first row from the second row. That's going to give us 0, negative 1, 1, 0, 0, 0. And we could put this all the way into reduced row echelon form by adding the second row to the first one to get 1, 0, 1, and then the second one would become 0, 1, negative 1, 0, 0, 0. So we have a free variable in the very last spot, so that tells us z equals z, or I think your book uses z equals t. Either one works. And then the first two lines are going to give us our two different expressions for the other variables. So we get x plus z equals 0, and y minus z equals 0. And so from that tells us that x equals negative z and y equals positive z. So that tells us that our vector is going to be negative 1, 1, 1, where we just take the coefficients of z of x, y, z, because that's 1z, or sorry, negative 1z, 1z, and 1z. And so those coefficients form our first vector. So vector 1 is going to be negative 1, 1, 1. Does that process make sense to everyone before we jump into the one that has a bit more algebra in it? Cool. So then let's do lambda 2 equals 1 plus the square root of 2. So let's see. Okay, so 1 minus lambda, that is going to be a negative root 2. So we got negative root 2, 1, 0, 0, negative 1 minus root 2, 1, 2, 1, and negative root 2 again. So this one, we need to figure out how can we row reduce that matrix to be able to get that one to a point where we can find the vector as well. So to start off, let's multiply the top row by the square root of 2. That is going to give us negative 2, square root of 2, 0, 0, negative 1 minus the square root of 2, 1, 2, 1, negative root 2. The reason I did this is so that we can then cancel out a significant part of the bottom row. So that's going to turn into negative 2, root 2, 0, 0, negative 1 minus root 2, 1. And then adding the first and third rows give us 0, 1 plus the square root of 2, and negative square root of 2. We can then add the second and third rows. So that's going to become negative 2 root 2, 0, 0, negative 1 minus root 2, 1, 0, 0, 1 minus root 2. And something tells me that we messed up. Because the reason I know I must have messed up somewhere is because we should always, if it was an eigenvalue, we should always have gotten a 0 row at the end. But this, where we got it to, is not going to have a 0 row at the end. So where did I mess up? Oh, I see where I messed up. Right here, that 0, that needed to be a 1. So that means that that was where I have a mistake. So we're going to have to fix that to figure out what our problem is. So that's a nice trick. If it was an eigenvalue, we should have gotten a row of zeros. Because we didn't, I immediately knew that we messed up somewhere. So that's something that can be useful to remember as well. So that is going to be a 1. So that didn't change here, so that's going to stay a 1. That didn't change here, so that's still a 1. And then when we added it to the other row, that's going to become a 1 in both of those spots, and that's undoing what we wanted. Okay, so that tells us that this step is not going to help us, so we should back up to the point where we can continue to work through it. Okay. So, starting where we're at then, we can still add the third row to the second row. That'll help. So that's going to give us negative 2 root 2, 0. 1, 0, 1 minus root 2, and then 0, 1 plus root 2, negative root 2. So to get rid of the 1 in the second row, let's add half of the first row. So negative 2, root 2, 0, 0, root 2 over 2, 1 minus root 2, 0, 1 plus root 2, negative root 2. And then, let's see, how might things cancel out nicely? Let's double the second row. So that's going to just become, that's just the square root of 2. And then this is going to be 2 minus 2 root 2. Let's see. And then I think dividing the second row by the square root of 2 is going to help. At this point, it's just trying to figure out how can you cancel terms. So we got root 2 minus 2, 0, 1 plus root 2, negative root 2. So to get something to cancel, we're going to want to multiply the second row by 1 plus root 2. 0, 1 plus root 2, and then let's see, what is square root of 2 minus 2 times 1 plus the square root of 2? We got root 2 minus 2 plus 2 and minus 2 root 2. So minus 2 plus 2 cancels, and so all of that is left with negative square root of 2. Perfect. Alright, and then from here, it's pretty straightforward to see that this is going to row reduce to a row with zeros. So negative 2, root 2, 0, 0, 1 plus root 2, negative root 2, 0, 0, 0. And so again, here is our free variable. And I am not going to put this into reduced row echelon form because that's just going to become a bigger mess. I am going to do this now that I've only gotten it to row echelon form because it is just as doable then. Again, we are going to say that z is free. So z is some variable t. And then we know that negative 2x plus the square root of 2 y is equal to 0. We know that 1 plus the square root of 2 y minus the square root of 2 z, or in this case t, is also equal to 0. So solving for y from the second equation, that's going to give us y equals the square root of 2t divided by 1 plus the square root of 2, which is valid but probably not of a form that we would like. So that's t times square root of 2 over 1 plus the square root of 2. To get rid of the addition of a square root in the denominator, multiply the top and bottom by the conjugate. So that's going to be 1 minus the square root of 2 over 1 minus the square root of 2. So that's going to be t times square root of 2 minus 2 all over, and then the denominator is going to be 1 minus 2. So that's going to be t times 2 minus root 2 all over 1. So y is 2 minus root 2 t. And then once we have that, we can then take this and plug it into the second equation to give us that negative 2x plus the square root of 2 times 2 minus the square root of 2 t is equal to 0. So 2x equals 2 minus root 2 times root 2 t. Divide both sides by 2. And then a little bit of simplifying will give us that x equals the square root of 2 minus 1 t. And so that tells us that our vector for v2 is going to be each of those pieces together. So we are going to get that v2 is equal to x is root 2 minus 1, y is 2 minus root 2, and then z is 1. So that would be our second vector, and then vector 3 is going to be something that looks very similar, except there's going to be some negative signs that change. Any questions with any of this that we just went over? Would anyone like to go over some other problems or other topics?
Can you go over how to find the basis of a set of vectors?
Yeah, we can go over that. Okay, so let's say that we have a set of vectors. So we got the vector 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got those 3 vectors, and we are trying to find a basis. So a basis, if you've forgotten, a basis has the requirement that they need to be, 1, all linearly independent, and 2, they all have to span the set. So the way that I go through finding a basis is I start by just looking at what is the first vector and start building a basis from there. So my first vector is going to be the vector 1, 2, 3. Is this currently a linearly independent set? Yes. Does it currently span the set? No. So I currently have linearly independent, but I don't have span. The next thing I need to do is I need to figure out what is a second vector that is still linearly independent. So I might say vector 2 is 4, 5, 6. Is that a valid choice?
When you say you don't have span, can you remind me what that means?
Yeah, so for span, so a set of vectors like v1, v2, and v3 span some set S if everything in S can be written like some constant times v1 plus some constant times v2 plus some constant times v3, where it's just linear combinations of our vectors in this set. So the vector v1 equals 1, 2, 3 does not span our set here because, for example, we can't write 4, 5, 6 as only scalar multiples of 1, 2, 3. It's just not possible for us to do that.
Gotcha. Thank you.
Yeah. So we might think that, okay, v2 is going to be a second linearly independent vector. The question is, sometimes the vectors might be a bit more complicated than that, and so we might not be able to tell, is it going to actually be linearly independent? And so that's one of the things that we have to check. One thing you could do is you could stick the vectors into a matrix as rows and row reduce to be able to figure out which vectors are actually linearly independent and which ones are dependent. But it does turn out that v2 is going to be a second vector. I will go over that.
Question about that, actually.
Yeah.
You said you would stick them in as rows and then row reduce.
Mm-hmm.
And so then, like, when you get a row of zeros, that means it's linearly dependent, right?
Yes, that means that your set was linearly dependent.
Does it work the same way if you put in the vectors as columns and you row reduce and you get a column of zeros or a free variable?
Yes.
Oh.
If you get a column of zeros, it works. If you get a free variable, if you get a free variable, not necessarily. I'm trying to think. That's a good question. My gut is saying...
Put them as columns.
Yeah, if you
So
put them as
just
columns and then row reduce, my gut is saying that if you get a free variable, that does not necessarily tell you that they're dependent, but I can't think of a counterexample. So what you're saying might be true, I just can't think of why it would be true right now. Yeah, that is a good question, and I'm not sure. Yeah, but if you row reduce and get a column of zeros, then yes. That is another way of approaching it. Wait, no, that is not true. If you put them in as columns and row reduce and get a column of zeros, that is not that is not going to be a valid that is not a valid way of approaching it.
Basically, we should just put them in as rows
Yeah.
and row reduce.
Yeah, put them in as rows and row reduce, and then if you get a row of zeros, that means that you have too many vectors for it to be linearly independent. Yeah, so currently v1 and v2, those are linearly independent vectors. But then if we try and figure out, if we add v3, is that still going to be linearly independent? And it turns out it's not going to be, because we can write v3 as 2 times vector 2 minus vector 1. It's not something that you would see immediately, but it is going to be something that's there. And so the way that we might be able to figure that out is if we put them in as rows. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And in the process of row reducing, we keep track of what we did. So to row reduce, so to get here, one thing we might want to do is to just make the first column only have a 1 in the top. So 1, 2, 3. Let's get the second row to have a 0 right here. So we are going to say that our new row 2 is equal to our old row 2 minus 4 of our row 1s. So that's going to be 0. 5 minus 8 is negative 3. 6 minus 12 is negative 6. To then move on to the next one, we still have 1, 2, 3, 0, negative 3, negative 6. This one is going to be our new row 3 is equal to our old row 3 minus 7 of our row 1s. So this is going to be 0. 8 minus 14 is negative 6. And then 9 minus 21 is negative 12. Which we can row reduce to get a row of zeros. By saying, okay, our new row 3, because our old row 3 is row 3 prime, our old row 3 is going to be row 3 prime minus 2 of our row 2s, which were a row 2 prime. And so we have successfully gotten down to this point. This is where we can then use our row reductions that we kept track of to figure out what the linear combination is to get rid of row 3. So we are going to combine all of these and try and solve for row 3 equals something in terms of row 1s and 2s. So if we can do that, that tells us our linear combinations. So row 3 double prime is equal to 0. So we know 0 equals row 3 prime minus 2 row 2 primes. Well, row 3 prime we already know in terms of row 3 and row 1. So this is equal to row 3 minus 7 row 1s minus 2 of our row 2 primes. But row 2 prime we also know. So that is equal to, we have row 3 minus 7 row 1 minus 2 times row 2 minus 4 row 1. And so at this point, we now know 0 equals that, and we are trying to solve for row 3. So we have 0 equals row 3 minus 7 row 1s minus 2 row 2s plus 8 row 1s. So we got 0 equals row 3 minus 2 row 2s plus row 1. And so row 3 equals 2 row 2s minus 1 row 1s. And these were our different vectors. Row 3 was vector 3, row 2 was vector 2, and row 1 was vector 1. And so that's how you can be able to go through and figure out what the specific linear combination is And so if you keep track of your row reductions, you're able to use those row reductions to tell you what exactly are the linear combinations that give you the linear dependence. Did that process make sense to everyone, or does anyone have any questions with this?
Can you just show where you go from here now?
Yeah, so from here, this tells us that vector 3 is actually, so this tells us that vector 3, this is not necessary. So it's not necessary to span. So that means if we remove this, the span did not change. But these other two vectors do still span the set. So if we only have these two vectors here, they still span, and we've shown that they are linearly independent. So that tells us that only these two first vectors, that is enough to be a basis. And so that's what that would show. If you started with a different vector, so like if you started with 7, 8, 9 as vector 1 and then used 1, 2, 3 as vector 2, then the vector 4, 5, 6, that would not be a necessary vector for the spanning and would be a linearly dependent one. So that would also be a different, also valid basis. But because we found that vector 3, 7, 8, 9 was unnecessary for the span, we were able to successfully remove it without changing what the span was, and so that would still, and so that's why just the first two vectors are enough to form a basis.
Sorry I keep asking these kinds of questions. It just helps me to remember things. What exactly defines, what is a basis of a matrix? Like, what does it represent? What do we use it for?
Okay, so a basis, there is no basis for a matrix. So that might be where your confusion comes from. A basis is only for a set of vectors. So a set of vectors has a basis. A matrix then depends on the basis to work. So a basis for a set of vectors is any set of vectors that satisfies those two requirements. If the set of vectors is linearly independent and spans the set that you care about, then it's a basis. So we'd have like a basis for R3, for example. R3 is not a matrix, but it's a set of vectors. So R3 is the set of vectors that look like this, x, y, z. And so one basis for this might be, so basis 1 might be the set 1, 0, 0, 0, 1, 0, 0, 0, 1. That is one valid example of a basis. Another basis that is just as valid is 1, 0, 0, 1, 1, 0, 1, 1, 1. That is just as valid of a basis. Both of these are linearly independent sets, and both of them span R3. We can write any vector that looks like xyz in terms of these three vectors from B1 or the three vectors from B2. That's what it means for it to be a basis. Did that answer your question?
I think so, yeah. Thank you.
Yeah, so like a matrix depends on a basis. So like for a linear transformation, for example. So if we have like t of xy equals like 3x plus 2y and then 2y minus x, for example, this transformation, this is a transformation under the basis 1, 0, 0, 1. because of how these are written, we're able to tell, okay, the first one is its own, the second one is its own thing. So that tells us that our vectors can be written as something with something only in the x spot, and then something with something only in the y spot. If we wanted to write the same transformation in terms of the basis, so if we wanted it in terms of the basis like 1, 0, 1, 1, for example, then the transformation would look like t of x plus y, y is equal to 3 x plus y plus 2y and 2y minus x plus y, or 3x plus 5y and y minus x. So this is the same transformation under different bases. And so they look different because they are acting under different bases. And so the basis that you're looking at is going to impact what the matrix of the transformation is going to look like.
Okay.
So both of those bases are perfectly valid. Sometimes one might be more useful than the other. The bases that look like this or like this, those are what are called the standard bases because they're the just ones that are the most natural for like R2, R3, R4. Those are the most natural bases for those, but they are definitely not the only basis.
Awesome. Thank you.
Yeah, good question. Any other questions that any of you have? Well, if not, I wish you all the best of luck on your test. I will still be here until 9, so feel free to stick around and ask questions if you have them. Yeah, go ahead.
If no one has any specific questions, I have been wondering if there's such a thing, kind of like a formula sheet for linear algebra that just kind of summarizes all these different relationships. It just feels like there's a lot of interconnected properties.
Mm-hmm.
And I would just love to like have a way to remember them all.
So I'm not sure if there is one of those, but we could like connect any of the ones that you're wondering what the connections are right here together if you want.
It's not so much at the top of my mind, like I can't think of certain things. It's just there's so many. I just wonder if there was a place to reference, but no.
Not that I'm aware of. Like I've drawn up my own connections.
Mm-hmm.
So like the way that I normally do it. So for example, if I was wanting to talk, like find all the connections with, for example, eigen vectors. So let's try and figure out what are all the different connections between eigenvectors. So the first place I would probably start would be like the definition. It's AV equals lambda V, and V is not the zero vector. So there's the definition of an eigenvector. And so from here, I can try and start to draw what are the connections that I see. Well, one connection is that this tells me that AV minus lambda V equals 0, which tells me that the determinant of A minus lambda I is equal to 0. Something that connects to this with determinants, I would maybe say, well, this connects with the fact that A minus lambda I is non-invertible. So that's something that connects to it from there. But then another thing that would connect is, if that is the case, then that means that A minus lambda I has a non-trivial null space. But if A minus lambda I has a non-trivial null space, that's also a connection to this saying that there exists, or I guess I shouldn't use that notation since I don't think that's in your class. That means that there are eigenvectors for A with lambda equals my eigenvalue. So like those are the sorts of connections that I would start to draw. Trying to figure out these different things. So like for example with the null space we can say, well, if something has a non-trivial null space, is that row reducing maintains the null space. It doesn't change it. So if it maintains the null space, that means it doesn't change. So I can just do row reductions to be able to find a easier matrix to find the null space of. And those are the sorts of things that I would be doing. I'd say, what are the different things? What are different ways to recognize the connections? And then I try and sort of connect those different things either with these arrows or implication statements to help me visualize better. If I have, so for example, if I'm trying to figure out is something a eigenvector, I now have several different ways that I can approach that problem to visualize what does that mean. So that's the way that I usually approach it, but I am not aware of anything that has all of those already connected.
Okay, awesome. Thank you.
You're welcome.
So would a good idea to study for each test and midterm, would it be good to like just go through a chapter and try to find and map out all of those connections?
That would be a good way to study. That's actually how I approach most math classes, is to try and find the connections. Because then even if you forget one of the middle pieces, you can say, okay, you can work your way through it basically by rebuilding the stuff that you learned in the chapter. So like if you miss the section on, I don't know, like if you totally forgot what it means for something to be non-invertible, but you remembered, okay, non-invertible had a connection to the determinant equaling 0. From there, you can then say, well, if it's non-invertible, the determinant's 0, there's a non-trivial null space, and so you can like make those sorts of connections. So if you needed to, you could be able to rebuild the material to solve the problem. So that's actually a really good way to study, especially for a math class, is to try and build the connections so that the connections are firm, so that even if you forget a specific term, you can be able to make the connections that you would need.
Awesome. Thank you.
All right. Who had the other question?
I was just wondering if you could zoom out so that I could grab a picture of.
Yes, absolutely.
And then I was wondering what it means to have a non-trivial null space.
Yeah. So a non-trivial null space, so that's a good idea. Let's connect that. So a non-trivial null space means that the null space has more vectors than just the 0 vector. Because every matrix has a null space, and the 0 vector is always in the null space. So if it's a trivial null space, that means that the only vector in the null space is the 0 vector. If there's anything else, then it's a non-trivial null space.
Okay, I think that makes sense.
Yeah.
And null space is like the area between vectors, is that correct?
No. So the null space, so the null space is the set of vectors.
Oh, I'm thinking of span, my bad.
Yeah, so the null space is the set of vectors where, so null space of a matrix A is the set of vectors where A times that vector is equal to the 0 vector.
Okay, I got you.
Yeah, and for example, another connection you might draw might be that, well, the null space, so connects to like this one and this one. the null space is a vector space. Vector space or subspace, depending on what you're referring to. And so that's another connection that you might be able to tie in if you need it. And so those are the different things that I would be doing for like the connections. Yeah. Do either of you have any other questions?
I think I'm good for now. Thank you.
I think I'm good. Thank you.
You're welcome. Best of luck on your test. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.